Our primary mission for this launcher recovery will be a safe ascent and a smooth descent to land with our payload safely sitting in the payload bay during flight. Along with that, we'll attempt to keep the rocket airborne as long as it can and verify the stability and efficiency of the design. We're going to talk about impulse. Now, thanks to this guy, we know that force is equal to mass times acceleration. Now, if you expand acceleration to change in velocity over time, and then slight time over and boom, we've got impulse. Now, simply put, impulse is the change in body's momentum or the area under a force time graph. You can see the thrust is proportional to impulse and is generated by pressurized water that comes out of the nozzle. This graph here shows you how the total impulse will vary if you have different water fractions. Originally, we used 4 fins at 90 degrees angle to one another. However, we found that replacing these with 3 fins at 120 degrees to each other does not affect stability, but reduces overall weight, and that turns into increase in maximum altitude reached by the rocket after launch. We then started to design the size and the shape of our fins. We landed on this current version with a lot of testings in Unity's wind tunnel, which reached reasonable stability in the shortest time and sacrifices the least altitude to achieve this, with even capabilities to touch down on the fins. This is followed by positioning testing, and we concluded that the optimal position of the fins was at negative 0.221 meters vertical position in Unity. The parachute is going to help us reduce the velocity of the vehicle drastically. The larger the parachute area is, the lower the terminal velocity is, and the longer the airborne period would be. This is because as more air is contacting the air, the drag caused by air resistance will be greater. Expanding our discussion onto terminal velocity, imagine you're on a building and you throw a ball from the roof. It's going to accelerate due to gravity, and there's going to be a subsequent drag force that is proportional to the velocity squared. The drag force increases with velocity as velocity increases with gravity, to a point where the drag force equals to gravitational force, and that max velocity is terminal velocity. Build quality is a key factor to keep the rocket reliable and our payload safe during flight. If the rocket is built by advanced materials, the weight can be reduced and can carry more payloads. Besides, the build should be tested to prevent any possible pressure leaks, and it should be able to withstand the launch pressure and descent drag. Weather also impacts the flight. The design is waterproof, which allows launches to happen in the rain. Though launches would likely be scrubbed if winds are too strong, the rocket should be able to land in light wind conditions. And under this condition, it's highly likely we won't have a perfect flight path as planned, which means there is no landing on its fins, but we will still make sure that it achieves a soft landing within the pad. In conclusion, our design is a well-made pointy rocket with 3 fins, a water volume fraction at 0.45, and a parachute diameter at 0.88 meters. This allows it to reach an altitude of just less than 23 meters before coming to a soft landing on its fins on a landing pad.